So today we want to talk about distributed high-throughput computing with particular emphasis on grid computing. And before we go into that, just a few words about me. Since Alain started that way, I thought I should too. So, oh yeah, 5 negative points, just so you know. So I've been working with distributed computing for a long time. You see there, 96. I started with my master thesis. It was not grid at that point, but it was still distributed computing. I got into the grid in 2005 and got more involved with OSG, especially in the gliding factory, in 2009. So I have been around for a long time, way too much probably, but that's it. That's life. And I'm also deeply involved with the gliding development and deployment. So this is why I will pontificate about glidings all the time, so you have to excuse me, but that's what I like about the grid. And last, I mostly work with high-energy physics, although I have been working with users from other fields as well. So just a reminder from yesterday, what is high-throughput computing? And high-throughput computing is essentially the concept of getting as many CPUs as you can to do your work, right? And to do that, use a batch system. You don't do it interactively, because that's the only way you can get something in a long period in an efficient way. So I don't know if you know who Miron is, but Miron Livni is the leader of the Condor project, and he is the technical director of the Open Science Grid. And I was made aware of this phrase that he said. Read it carefully, because I think that's what this phrase really gives you a sense what high-throughput computing is really about. High-throughut computing is about extending the compute power of your own machine. You could do all the work on your own machine, but then it would take a large number of work clock days, years, centuries to do your work. So to finish your computation in a reasonable time, you have to expand the capacity beyond your own machine and using temporary resources somewhere else in order to accomplish the job. You don't need to go outside, but you would have to wait a long time if you didn't. So it's in your best interest, if you have a problem that is big enough, to go out and seek resources. And just a reminder, yes?
If you have a problem big enough, but if you can break the problem too, if you cannot break the problem, can you still talk about using high-throughput computing?
Well, if you cannot use more than one CPU at a time, you will wait a long time. So, yeah, there are limits to what you can do. But if you can use more than a single CPU, think how to do it, because it is in your best interest. Let's just sit down and wait. Life is long. It's not a big deal. You have maybe 100 years to sit around. So maybe by the time you retire, you get your Nobel Prize. But if you get it while you are young, it's probably better. More questions? No? Going on. OK. So yesterday was HTC. Today it's distributed HTC. And you may wonder, what is distributed HTC? HTC is distributed by nature, right? Every time you do high-throughput computing, you go distributed. What I'm talking about today is something that is massively distributed, something that is really big. And in particular, more than you can afford in a single place. You may have a large cluster on site, but that would not qualify for distributed high-throughput computing. It's just plain old high-throughput computing, as Condor has been doing for a long time. So the distributed high-throughput computing I'm talking about is using more than one cluster, essentially. You have your own cluster and a couple more clusters, possibly somewhere around the globe you want to use. So why is this different? Why we have a separate lecture on distributed high-throughput computing compared to just plain old high-throughput computing? The reason is that you don't have a single system anymore. Now you have to think about all the problems that come from the fact that you actually have to go to many different places. And the first thing is while on the local cluster you may have a shared file system, it's pretty much given that that will not be the case when you go to multiple clusters. Each one may have a local shared file system, but between the three of them, there is practically zero probability they will have the shared file system. So file movement will need to be considered. The different clusters are likely operated by different people. And as such, they will have different policies. They may even use different technologies. While yours is Condor, somebody else may have PBS, the next one will have LSF, and you will have to use all three of them somehow. And the accounts you will have there may be different. So security comes into place as well. And I already mentioned the different technologies. And obviously, once you get to multiple clusters, it gets harder. Like getting from your desktop to using a Condor cluster, which has many nodes locally, it's harder. So going from a single cluster to many clusters is getting harder. So as you go from your desktop to the local cluster to a truly distributed high throughput computing, expect more pain. But if you need it, it's well worth it, I would say. So if you don't need it, don't use it. But when you do need it, be prepared to suffer a little bit, but the gains can be massive. So why do people even do distributed high throughput computing if it is painful? There are many reasons. It goes from the practical. I simply cannot put all the machines in a single room. There is simply no space. I have to distribute it across campus, for example. They are political. You go to NSF, say, my science needs this amount of money. And they say, oh, we know a nice place in New York that has space for it. We'll put it there. But I'm in Wisconsin. We don't care. So you have to live with that. They're economical. You simply may not be in a good position to do it in an efficient way. If you all you can afford, maintaining computers costs in human time. So if you don't have a system administrator, and you have to hire one to handle 10 machines, that's extremely expensive. Those 10 machines could be managed essentially for free at another computing center for you. So sometimes you just don't have a choice. And then you have the opportunistic reasons where somebody else may have some cycles lying around that they are not using. And why not use them? They may be happy to keep their CPUs occupied for free or maybe for pay. But there are places around the world that have CPU cycles that are free, waiting for somebody to use them one way or another. So if you want to use them, you have to be ready to do it and know how to do it. So here are 4 classes of distributed high throughput computer as we see them in real life. We start with campus-wide scheduling, and University of Wisconsin is great as an example. Essentially, they have different departments having their own clusters, and they just talk to each other. They are effectively independent, but merged together in such a way that look like a single one. You have the scientific grids, like the open-size grid, TeraGrid, or EGI, and I'll go a little more in detail on that. You have the hosted service, like Rackspace, and cloud computing, which is something relatively new with Amazon EC2. And I'm going a little bit more detail on each of them. So the campus-wide scheduling is something that connects multiple high-throughput computing clusters together in a relatively tightly connected system. There is a high trust between all these clusters. The sysadmins probably know each other face-to-face. They meet together often. They coordinate policies to a certain degree. And you may even have somebody on top that controls all of them, like the CEO or the dean or something like that. And usually, they use the same technology. Not necessarily, but very often. So life is much easier because everything is much more uniform. And from the user point of view, it doesn't really feel like a truly distributed high-throughput computing. It seems sort of like a single cluster, even if you may have really different islands operated by different people, but very well connected together. But then you go beyond that, and you get to scientific grids, like the Open Science grid, which is US, wide, and beyond. We have an example from Colombia, who is part of Open Science grid. But OSG, the first approximation is it's US-based. So you have sites from coast to coast. And of course, in this case, people just can't talk to each other. The distances are too many. There are too many people involved. Here I have approximately the number. It's a little less than 100 sites, several thousands of users. And you can imagine things get more complicated in this way. And just to make life more difficult, there are many technologies involved. On Open Science Grid, we have everything from Condor, PBS, LSF, SGE, and some sites probably want to do something else, but we are trying to convince them not. And this is because they may already have something in place. Many sites just don't say, oh, today I want to join the Open Science Grid. Somebody gave me $2 million, I built everything from scratch. No, they have something already in place, and they say, well, we have this thing in place. Wouldn't it be nice if we joined a bigger organization? So it's the way around most of the time. So that makes for a very heterogeneous system, and we have to live with it. Next thing I said is hosted computing, and this is usually pretty commercial offering, where you can lease a server for a certain amount of money a month. One example is Rackspace. You go to there, or GoDaddy, you give them $400, and you have a machine for a month. Do whatever you want with it. It's yours. At the end of the lease period, they cut you off and lease it to somebody else. But it's computing like any other, and it's a very convenient solution if you know that for the next 2 months you will need a lot of computing power. That's the way to go. It's much cheaper than build your computing center. And final, it's the cloud computing, which is the new buzzword of the day, or the month, or the year, or the decade, whatever. We'll see how long it will last. But it's effectively a mix between hosted computing and grid computing. It's job-based like the grid. The only difference is that the jobs are virtual machines. So you effectively submit a job that contains the whole system image, including the operating system. But on the other hand, it's hosted. Somebody else hosts it for you, and you pay. You give it the money. They're happy to take it and give you the machine for an hour if you want. No big deal. Amazon price, I think right now, is 8.5 cents an hour for a CPU. So it's nice, right? It's just that you don't get a whole machine. You just get a portion of it in a virtual machine, and you effectively schedule it with a batch system. Right. So for this talk, I'll concentrate on grid computing. I will not talk anymore about the clusters on campuses. I will not talk about hosted or cloud computing. I will get back to the cloud computing this afternoon. But for now, let's just switch back to grid computing. So grid computing, effectively, you can think of distributed high-throughput computing over wide area networks. That's pretty much what it is to the first approximation. Now, the major difference is that you are not really allowed to log into the scheduler. It's not like here you log into VDT ITB and submit. At least most of the time you don't. You need a way to submit a job from one state to another, get the jobs in the queue, and they will eventually run. And what this thing in between, it's usually called the computing element in the OSG speak. I prefer the word gatekeeper, but this seems to be the standard word to call it. And C, it's very short, so it's very nice for the slides, if nothing else. So what is the gatekeeper or the C? You obviously have many options. You can go directly with a native system, like Condor itself allows you to submit to a SCAD from remote. You don't need to log in, for example, in VDT-ITB. You could do it from your laptop and submit to VDT-ITB. It will work. Of course, there is always SSH. And for example, TerraGrid sometimes just tells you, just log in and submit. They have also the true grid gatekeepers, but they even allow SSH. On Open Science Grid, SSH is forbidden to a large extent. Some sites allow it, but it's rare. So the grid gatekeepers, there are several technologies that do this. Open Science Grid mostly use Globus. We are looking at CRIM. We have looked at ARC. But all three of these are used somewhere in the grid. And why we use the grid gatekeeper, something that is dedicated for the grid, is mostly because they hide side details. And here I have a little more details. The reason, as I said initially, when you go wide area networks grids, likely you will have different technologies on each site, because sites simply grow organically and then at one point in time join the Open Science Grid. It's not the way around for most sites, although some sites do start fresh just for Open Science Grid. So the grid gatekeeper really, what it does, it provides an abstract API that you talk to it and it will do the magic to talk to the real local HTC system that is installed inside. And it will nicely integrate with whatever the sites have decided to deploy. With limits, but of course. But that's to the first degree. And this makes life easier for the user because you don't need to know the site details. All you need to learn is the grid commands. And if it is PBS, Condor, LSF, SG, you don't care. If you went with the distributed HTC system native commands, you will need to use PBS commands for one side, Condor for another, LSF for the third one. It would be a mess, right? Doing grid submit, it's much easier than doing Condor submit, B sub, I don't know what LSF is, and so on for different sites. It makes life a little easier. And as I said, most grid site communities these days use grid gatekeepers one way or another. So the grid C, it's really just an abstraction layer. So that if all the sites use the same grid technology, user needs a single client to talk to all of them. And it doesn't matter if it is Condor, PBS, or LSF behind. It will just work. So one step further to make life easier for the users is to use Condor. Guess what? Condor is a universal client. You can use Condor to essentially submit to everything else. May seem weird, but this is what it is. Condor by itself, it's not only a bed system for local clusters. It can work in a different mode, also usually known as Condor G, where it can delegate, you submit to Condor, and Condor will talk to essentially any other system out there that is widely deployed. Not all of them, but a large fraction of them. All you need to do is essentially provide, instead of using a vanilla or standard universe, use the grid universe and do some other magic that I will explain later on. And Condor will do the trick and talk to the remote systems. You will use exactly the same commands, Condor submit, Condor queue, and so on. And so from the user point of view, it's very similar to submit to the local vanilla universe. But it's very, very different under the hood. And let me explain why. Condor G doesn't really manage the resources, right? When you have a vanilla Condor, Condor manages both your jobs, but it manages also all the worker nodes. In the grid world, it manages just your jobs. The resources are managed by somebody else. So what Condor G does, it just forwards your requests. So it's just a translation layer so that you submit to the local scheduler, and Condor G will convert it to whatever grid technology needs to be done and submit to a local scheduler remotely. But that's it. It doesn't control the worker nodes. So you have no equivalent for condor status, because all it can know is the job is running or not, but it doesn't know what state are the grid resources because it doesn't own them. And there is no matchmaking for exactly this reason. It is not managing the resources, it's just forwarding them. So the user will explicitly need to specify where it wants to go, what grid protocol the site is using, and how to get there. There are some limited resource selection available with some external support, and I mentioned it a little bit later, but it's not very extensive. So when you talk Condor G, think about it just a forwarder. It's just somebody that manages your queue so that you can submit 10,000 jobs and go home, sleep, and come back in the morning and see if they are all done. Condor will do all the forwarding, monitoring, error recovery to a certain degree. But no Condor status, no matchmaking. And yes? Well, because there is no such thing as a grid submit. The grid submit was just an abstraction for the slide. If you go to Globus, or Cream, or Arc, or Condor C, or whatever, over the wire, they talk a completely different language. So you have to tell it which language to talk, because Condor cannot just discover it. You need to tell it. On OpenStansGrid, it's pretty much Globus, so it's not a big deal. And all our examples will be Globus, so it's trivial. But if you go to Europe, these days, you have a mix of Globus, Cream, and Arc. And we will actually see in the exercises, just for fun, I will have to use Condor C, which is Condor to Condor. And you tell Condor, use the grid universe and talk Condor protocol. More questions since we are here? No? OK. So as I said, no matchmaking. So if you have no matchmaking, it means that you are responsible to be the matchmaker. So if you have thousands of jobs, and let's say 3 sites, you have to decide how to partition them. How many will go to this site, how many to this, and how many to this? Condor will not help you. You are responsible for doing it. Condor will do all the forwarding once you decide, but it will not partition it for you. So why is partitioning a hard problem? The reason is that you don't really know what's going on behind the scenes at the grid. Just because a grid has 1,000 CPUs, it doesn't mean that you will get 1,000. You may get 0, because there are so many other users that are using that site, and you are trying to use it in an opportunistic manner, that you may get a CPU a month. There are sites like that. And another site that has 10 CPUs, but you own it, may get you all 10 CPUs for a month, and you will get way, way more in a week from that small site than the big one. This is because you don't really understand what's back, neither what is actually being used, not the policies, and oftentimes not even how many CPUs they have. It's pretty much a black box to a first degree. You would love if somebody would partition it for you. And there are some products out there. One is July WMS that some people have asked me yesterday, that essentially tries to guess what is the best way to partition your jobs. But their success have been limited at best, I would say, exactly because the grids are pretty much black boxes. And trying to forecast the future, you would need to be an Oracle. Not Oracle, the company, but really the Oracle from the Greek times. And that's pretty much impossible. So they do a decent job, but far from being optimal. And that's all. So time to do some exercises. Of course, ask questions anytime, now, later. Any questions for now? No? OK, so for the exercises, I want you to move in front, make groups, possibly 4 per table. I know that we are 25, so one table will be 5 people. And all the exercises are in group. So start moving in front and make the groups. I hope that everybody has a laptop that can last at least an hour. So that should be fine. So let's start.